In the statistical learning module, the first part that we talk of is Introduction to Statistics. The things that we are going to cover here are basic statistics, the introduction to the basic terms, what are the variables, what is the measures of central tendency, the mean, median, mode, the measures of dispersion, range, standard deviation, variance, and we'll discuss them all. Then we'll talk what's a population, what's a sample. We'll talk about what is Chebyshevs Theorem. Then we'll move to probability. We'll start with the set theory. We'll talk basics of probability. We'll see probability from three schools of views: the classical, the frequentist, and the Bayesians. After that, we'll move to terms like random variable, expected values, variance, the distribution, the discrete distribution, the continuous distribution, and then their probability density function or mass function, their cumulative distribution function. This is all that we are going to cover in basics of statistics. So let's start. What is statistics? Statistics is the science of collecting, organizing, presenting, analyzing, and interpreting data to help in making effective decisions. Statistical analysis is implemented to manipulate, summarize, and investigate data so that useful decision-making information results are obtained. Suppose you're running a business, an online cloud selling company, and you want to send a campaign to your customers. To a certain set of customers, you send a campaign. To others, you don't. And you want to know whether the customers are going to buy based on campaign or not, whether the campaigns were effective or not. Then how do you design that experiment? How do you design whom to send, whom not to send? How do you figure out how many of them to send? And once it has happened, and suppose the customers who got the advertisement clicked on it and purchased a little more as compared to the customers who did not get the advertisement. Now, how do you establish that even if the advertisements were not sent to the customer would have still bought, those particular set of customers would have still bought more? To answer all these questions, we do statistics. So there are two kinds of statistics. One is descriptive statistics and the other is inferential statistics. Descriptive statistics is a method of organizing, summarizing, and presenting data in the informative way. You have all the data, like how your business has been going on, how much inventory you keep, how many customers come to your store, in which month has it been more, on what day of the week it occurs more, which product are usually sold more at what point of time, on what hour is your product sale more, what kind of customers come, is it like female customers come more at this point of time or male customers come at more this point of time, people with children come more, cigarette buyers come more, beer buyers come more, or grocery items buyers come more. All these questions based on data are answered by descriptive statistics, as opposed to inferential statistics, which is a different kind of statistics altogether. Recently we had an election in a state. Now you're not going to ask every person whether they voted for one party or the other, but you want to figure out. So you select a sample. You decide the sample size, and based on that sample size, you try to infer which party is going to get more votes. You try to infer whether a person is lying or telling the truth. So that becomes inferential statistics. So the population in that case would be all the individuals of that, say Gujarat, where people voted. And sample would be those people to whom you went and asked, hey, are you going to vote for party A or are you going to vote for party B? The population can be finite or infinite. Say you want to talk of all the stars in the universe, all the planetary systems in the universe, all the solar systems in the universe. So you are trying to make an inference whether there are aliens living over there or not. So that population, as of now, is infinite. You pick a sample and you figure that out. You can say that population of India is finite. We know how much it is. But for practical experimental purpose, it is logically not possible to go and ask each and every individual what is their opinion on a certain party or on a certain idea. So in that context, that also becomes an infinite. So you choose a sample out of that. What would be a finite population? Suppose you have number of customers. You are a telecom company. So there are, you have a subscriber base. You know all of them. You can send messages to all of them. So that is a finite population. However, even though sending SMS or sending an email may not be a very costly operation, still you would refrain from doing it. Still you may prefer to pick up a sample to make more sense of the data for better analytical tractability. The other basic terms, while laying the land of statistics that we are going to use quite often that we need to know are variable, data is singular as well as plural word, experiment, parameter and statistic. Now what's a variable? Suppose you are a person who runs an ATM company. You have ATMs all over India and you have to put money in morning or at any point of time every day in that ATM so that people come and withdraw the money, and at no point of time there is no money in the ATM, while at the same time you want to optimize how many people are going to come to the ATM and you don't have to go many times to keep filling the money. So what are the variables here? The variable here are how much does a person withdraw, at what time of the day the person withdraws, how many people come to that ATM on a given day. All these are variables. Are they males or females? What is their educational background? Suppose people come to their shop, how many times they come, how much money are they going to spend, how many people walk into your store, out of them how many buy, how many don't buy. These are all variables. What is their age bracket, whether they are smokers or not, whether they follow certain kind of music or not, whether they wear certain kind of dress or not. All these are different kinds of variables which gets us idea about the things that we are going to analyze. Next is data. So now what those values that you put in those variables are data. Person 1 came and withdrew 10,000 rupees. Person 2 came and did shopping for 3,000 rupees. Person 4 bought a Louis Vuitton jeans. Louis Vuitton bag. Person 5 bought a diesel jeans. And so on and so forth. The age of person 5 was 25 years old. His income was 20 lakhs per annum. Person 7 carries an iPhone as compared to person 8 who carries a Samsung phone. So individual data is singular, and if you have multiple data of the same person and multiple rows of them, that becomes data in plural. Now what's an experiment? What we talked of just now, that you send a campaign, a set of campaign to people, whether they're going to buy more or not based on that campaign. Your experiment can be whether I should put this advertisement on television or on your Google or on your Facebook or on your Instagram or while you're using any particular app. Deciding all this is an experiment. How do you design that experiment? To ask the right questions, to get the answers to your questions, you design an experiment. The parameter is a numerical value which summarizes the entire population data. Like, what is the population of India? That's a parameter. What is the average age of all the Indians? That's a parameter. What's the average height of all the males in India? That's a parameter. What's the average height of all the females in India? Another parameter. What is the average income of all the individuals? That's a parameter. What is a statistic? Now, you don't know average height of all the citizens in India. You take a sample. You pick some people from Chennai, some from Madurai, some from Allahabad, some from Jammu, some from Delhi, some from Mumbai, Kolkata, Bangalore, Hyderabad, and so on and so forth. You pick people from different age groups. You pick people from different gender. Okay? And you go and ask them their height. Based on their average height, can you say what's the average height of India? That's statistical inference. But the average height of your sample is statistic. The standard deviation of your sample is statistic. So we are clear of all the basic terms. Let's say which one we just did. We talked of variable, we talked of data, singular and plural. We talked of experiments, we talked of parameter, we talked of statistics, we talked of population, we talked of sample. Moving on, what do you think is the most important thing in statistics? It's the data, it's the variable. You need to understand what kind of data that it is. Data can be of different categories. In all data analytics, we are trying to analyze data. It's about data. We need to get an idea that We need to develop a language of talking about that data where we can communicate, So we need to define certain terms which makes us easy for us to talk about those data. So the variable, like I talked of, what is one variable? How many people are going to come in the store? That's a variable. Is that numerical? Is that non-numerical? Like, can 10.33 people come to my store? Can 100.77 people come to my ATM? No. So, a fixed number of individuals can come to my store. So, that's a quantitative data. That's a numerical, discrete data. What was the gender of the person? Male or female? Is male better or female better? There is no answer to such question. What was the color of the dress the person was wearing? Was she wearing a red dress or a blue dress or a green dress or yellow dress? Is any color more important than the other? No. Is it a numerical data? No. But it's still a data. Okay. So there are different kinds of data. The first major qualification of data is qualitative and quantitative, where there is no number involved. That's qualitative data. The red, blue, yellow, green color dress is qualitative data. Whether the person was wearing cap or not is qualitative data. You can write yes or no. Or you can write yes as 1 and no as 0. Just because you have replaced yes with a number and no with another number, that does not make it a quantitative data. It still remains a qualitative data. Next is quantitative data. Quantitative data can be of different types. As I've already talked, the salary of a person, the age of a person, the number of people coming to an ATM, all these are quantitative data variables. They have numerical value. So the variables, two broad classification, qualitative and quantitative. Qualitative have not two categories, nominal and ordinal. Okay. So suppose the person is male or female. You put male as 0 and female as 1. Okay. That's a nominal data. No one is better. There's nothing that's higher than that. Whether the person was wearing a sweater or a jacket, you put 1 and 0, or none of them as 2. These are all nominal data. You can't say 2 is better than 0. That's just way of representing that this was there or that was there. The other category is ordinal data. Suppose I want to ask, how was your cab experience? You rate as 1, your friend rate as 5. It's very difficult to say that her 5 was better, 5 times better than your 1. Okay. But it's quite clear to say that her experience was better than yours. So here you can say that one thing is better than the other. Okay. Such kind of data is called ordinal data. Okay. So qualitative variables are two types, nominal and ordinal. I'm using data and variable as interchangeably, but data is the individual element of those variables. In case of quantitative variable, it's again of two kinds, discrete and continuous. Discrete are one which are natural numbers, like 5 people can come to my store. 100 people can be sitting in an aeroplane. You cannot have 100.33 people coming to an ATM. So these are discrete numbers. What are continuous numbers? What's the weight of a person? Now you can measure the weight of a person till 100 decimal digits. A person's weight can be 72.3745238 kgs. Okay. So these are all real numbers. So quantitative data, quantitative variables are discrete and continuous. Discrete are natural number, continuous are all real numbers. So we have talked of different kinds of variables. We've talked of quantitative and qualitative variables. We now know what are nominal variables. We know what are ordinal variables. We know what are discrete quantitative variables, and we know what are quantitative continuous variables. Now we are going to talk of something called measures of central tendency. If you have a lot of data, what is that one thing that can tell you about the data? If you have lakhs and lakhs of rows of data, and you want to tell someone in one word, what would that be? So the first basic thing on that is measures of central tendency. There are 3 of them: the mean, the median, and the mode. Most of you would have heard of this. Nevertheless, let's discuss them. What is a mean? Suppose I have some data, some marks of blood pressure, some systolic blood pressure of 7 middle-aged men. They are 151, 124, 132, 170, 146, 124 and 113. How do I calculate the mean of these 7 data? We sum them all up and we divide it by 7. So x bar is equal to sum of these values divided by 7, which gives us 137.14. So 137.14 is mean of this set of data. What's a median? Median is the guy who's standing right at the middle. If I take a class and ask them to stand height-wise, the shortest guy at position 1, the next shortest at position 2, the third one at position 3, and so on, say till position 9, there are 9 individuals. The tallest one is at the 9th position and the shortest one is at the 1st position. So who do you think lies right at the middle of all this? The 5th guy. So the height of the 5th guy is the median of that data. In our current case, where we have this systolic blood pressure, which is the one which lies at the middle. The smallest is 124 and there are 2 of them. The highest is 170 and that's at the end. And how much data we have? 1, 2, 3, 7. 7 records I have. So then I have to see that which guy is lying at the 4th position, either from the start or from the end. That guy over here is 132. Now what happens if there are 8 guys over there? You have 2 people lying at the middle. The 4th guy as well as the 5th guy. Then we take the value of the 4th guy and the value of the 5th guy and take the average of that, and that becomes our median. Last but not the least is the mode. So say I have a class who has they have written an exam and the marks varies from say 60 to 70. 100 student class, someone has got 61, they say 10 students have got 61, 5 have got 62, 7 have got 69, 10 have got 70 and so on and so forth. Then which is the marks that is most common among all the students? Suppose in the class of 100 students, there are 40 students who have got 67 marks. Okay, and the next number say 63 is got by 30 students. So 67 becomes our mode. The number that occurs most number of times, the number that has the highest frequency is the mode of the data. Mean is the average, median is the middle guy, mode are those guys who have maximum in number in the value. So they also have a relationship among them. A simple mathematical relation is mean minus mode is equal to 3 times mean minus median. Written again, if you rearrange the values, you can try it yourself. Mode is equal to 3 times the median minus twice the mean. You don't have to remember this, but it's good to know that there is a relationship among the 3. It's a rough relationship, not an exact one. So if you know 2 of the values, you can approximate the 3rd value. We have discussed the measures of central tendency. Now we move to something called measures of the dispersion. Suppose you have 2 classes, section A and section B. In section A, there are say 100 students. In section B, there are say another 100 students. Okay, and then each of those 100 students in section A have got 50 marks each. So what will be the average of section A? It will be 50 plus 50 plus 50 added up 100 times divided by 100. What would that be? That would be 50. Suppose in section B, there are, 50 students who have got 0 and there are 50 students who have got 100. Okay. So what will be the average of this class? The average of this class would be 50 into 0 plus 50 into 100 divided by 50. That is again equal to 50. So what's happening here? I have data of 2 classes. The mean is same, but the data is very different. I need some other value to tell me that. And that value is about the spread of the data. How long my data is spread. Is it like all of them have got 50 marks? Or some of them have got 0, some of them got 100, some got 90, some got 10, 80, 30 and so on and so forth. So though the mean of the data is same for both the class, but those classes are very different. So first such measure is range, and the second such measure of dispersion is the variance or the standard deviations. They are related. What is the range? Range is the maximum value minus the minimum value. So in a class, suppose the highest marks is 70 and the lowest marks is 10. Then what will be the range of that class? 70 minus 10 equal to 60. So that's the best minus the worst that we have got, the difference of the extreme value, and different ways to say this, but essentially it's the maximum minus the minimum value. How do we calculate the variance or the standard deviation? Suppose I have 4 data points, say 10, 20, 30, 40, 50. What will be average of all this? Sum of all this, which should be 150 divided by 5, that's equal to 30. So 30 is the average of this class. But to calculate the standard deviation, I do 10 minus 30 equal to minus 20, 20 minus 30 equal to minus 10, and 30 minus 30 is equal to 0, 40 minus 30 is equal to 10, and 50 minus 30 is equal to 20. I take square of each of them. What's minus 20 square? It's 400. What's minus 30 square? It's 900. Sorry, minus 10 square, it's 100. What's 0 square? 0. 10 square, 100. And 20 square, 400. I sum them all up and divide it by either n minus 1 or n, we'll come to this later, to get the sample variance. N minus 1 when we are using sample and n when we are using the entire population. So that gives us the variance. You know, in this figure you can see that the first one, the spread is more. These 3 balls are on too far left and 3 balls are on too far right, and there's nothing in between. In the second data, 3 balls are left but not so far from the middle, 3 balls are on the right but not so far from the middle. So in which one do you think the variance, the spread would be more? Obviously in the left one. The standard deviation or the variance of the left sample will be higher than that of the right sample. The standard deviation is nothing but the square root of the variance. You take the variance, you take the square root and you get the standard deviation. Now let's come to population versus the mean. When we have the entire population data, we take each say of the entire height of all the males in United States whose age is greater than 25. I take each of their height, I sum them all up, divided by the number of people, male person in US who are greater than age 25, I get the population mean, which is denoted as mu. But instead, it's not possible to get the height of every individual. So what do? I take sample. I take some from Washington, I take some from California, some from Texas, and all the 50 states, and based on how much people stay in that state, and I calculate the average of that. That is x bar. Okay, so there is population mean. Population mean, it is a standard practice, is always denoted as mu. The sample mean is always denoted as x bar. So if you have to fill this table, for population n, size is denoted as capital N. For sample, the sample size is denoted as lowercase n. The population mean is denoted as mu and the sample mean is denoted as x bar. Similarly, we have population standard deviation and we have sample standard deviation or variance. The population variance is denoted as sigma square and the sample standard variance is denoted as s square. When we calculate population variance, we divide by n, summation all the data values xi minus mu the whole square divided by n. And when we calculate the sample variance, instead of dividing by n, we divide it by n minus 1. We'll come to this later, that why we are using n for population and why we are using n minus 1 for the sample. For the time being, let's keep it that way. And it's not difficult to figure out that the population standard deviation is written as sigma, that sample standard deviation is written as s. Here we go. The population mean is denoted as, population variance is denoted as sigma square, population mean is mu, and the population size is capital N. Kindly note that when we use population, calculate the population variance, we do not subtract the 1. But when we calculate the sample variance, we always subtract 1 from the sample size. This is not what we do when we calculate mean. When we calculate population mean mu, we divide it by capital N, lower uppercase n, and when we calculate the sample mean x bar, we divide it by n. In that case, we do not subtract 1. But when we calculate the samples variance, we always subtract it by the sample size by 1. As already discussed, the standard deviation is sigma, is root of the variance for the population, and the sample standard deviation is denoted as s, which is the square root of the sample variance. So, before we go in detail of this, let's take some cases. Suppose I plot the data, two sets of data. One is which has very less standard deviation and one which has very high standard deviation. They both of them have the same mean. So there is this data and there is this data. Which one do you think? Case A or case B? Suppose both of them have mean as say 50 and 50. So which one has more spread will have more standard deviation. Which one do you think has more spread? The case B has more spread, which will have the higher standard deviation. There is a very important theorem called the Chebyshevs Theorem. It helps us a lot in doing statistics. Once we go to second or third session, or maybe fourth, we'll figure out why it is so important. But before we go there, we need to know what that theorem says. The theorem says that if I take all the data and calculate the mean and calculate the standard deviation, what we will always see is the proportion of observation in any sample that lie within k standard deviation of the mean is at least 1 minus 1 by k square for k greater than 1. Let's try to understand this. Suppose I have a data whose mean is say 50 and the standard deviation is say 10. Okay. So how many of my data points will lie, a class which has average marks as 50 and there are 100 students in that class. So I want to know that at least how many students of those 100 have got marks between 40 and 60. Then Chebyshevs theorem comes to our help. Say standard deviation is not 10 but it's 5. Okay. So we have two standard deviations on the left side and two standard deviations on the right side. So 1 minus 1 by 5 square. So 1 minus 1 by 25 as a fraction. Okay. Sorry, 1 minus 1 by 2 square. So 1 minus 1 by 4 is how much? 3/4. 3/4 of the data will have marks between 40 and 60. In a class of 100 where the mean marks is 50, the standard deviation is 5, 3/4 of the students will have got marks between 40 and 60, or in other words 3/4 of 100 is 75. 75 of 100 students will have their marks between 40 and 60. That is what Chebyshevs theorem tells us, and it is extremely helpful in figuring things about the data. Suppose you want to launch a new product. You know that the person's buying capacity is say $50,000 and the standard deviation of those people is say $5,000, and you think that if my product sells around say 75,000 of my new smartphone sells, then I'll break even in the market. So then, you want to figure out that, what price range should I put my mobile phone on, so the new phone in, so that my cost is covered, but I want to optimize my profit as well. Then you would know that, okay, around 75,000 people are there who would be willing to spend between 40,000 or to 60,000 for such a product. Now we move on to probability. To do that, we need to first understand what is set theory. We'll do very basics of set theory, assuming that you have done, this will be a revision, assuming that you have done basics of that in the school. So how do we define a set? Suppose I have a class. The class has 100 students. That is my universe. That's what I am talking of. Those 100 students. I denote it as universe. Out of those 100 students, 60 students play baseball. So how many of them do not play baseball? That is 40 of them. So 60 of those students lie within this circle and 40 of them lie in this shaded region. That is my Venn diagram for my set. My set 60 is the one who are the ones who play baseball. So say Alex, John, Bill, and so on. So P consists of all the people who play baseball. P dash consists of all the people who do not play baseball. The number of people in the set P is 60. The number of people in P dash, which is P complement, is 40. So this is what helps us in putting things in diagram, and this is very helpful in figuring other things out as well. Let's look at the second diagram. Now we have two games that is there in the class. My class consists of 60 students, 100 students, so my universe is 100. There are two circles over here. Say the circle A represents all those who play baseball, and the circle B represents, say, all those who play basketball. Okay. Now, can there be some people in the class who do not play either baseball or basketball? Yes, there can be. Can there be students in the class who play both the game? Yes, there can be. Okay. So in the class of 100, say the number of people who play baseball is 60. The number of people who play basketball is 30. And the number of people who play both the games is 10. So how many people play only baseball? They do not play basketball. That is this region. So that is 60 minus 10. There are 60 who play baseball. Out of those 60, there are 10 of them who play basketball as well. So how many are left? 60 minus 10, 50. They come over here. Similarly for basketball, in that same class, if I ask, hey, do you play basketball? How many of them would raise their hands? 30 of them would raise their hand. Out of those 30, I separate them and I ask them, how many of you play baseball as well? Then out of those 30, 10 would raise their hand. So how many are left? 20 of them. So there are 20 students who play basketball but do not play baseball. There are 50 students who play baseball but do not play basketball. And there are 10 students who play both the games. There are 60 who play baseball, there are 30 who play basketball. So how many remaining? How many students are there who do not play any of these games? The class size is what? It is 100. Out of them I have accounted for this 50, this 10 and this 20. That's add up to how much? 80 of them. So how many of them left? 20 of them left. And what do? Nothing. They don't play baseball, they don't play basketball. Maybe they play some other game. Okay. So there are different ways to denote things in a Venn diagram. In figure 2, this shaded region is called intersection of set A and set B. It consists of all the people who play both baseball and basketball. In figure 3, this is called A union B. Okay. This is all the students who play either baseball or basketball. If you understand the difference, intersection is they play both the games. Union is either one of them, at least one of them. Okay. Suppose I have a customer and the customer comes to buy a camera and he also comes to buy a watch. So there are some customers who would buy both the gadgets, one camera as well as watch. So that is this intersection region. And I want to know that my shop sells only two things, either camera or the watch. I want to know how many people purchase from my shop. Then that is this union region, the second part. Okay. And what about this unshaded part? These are those people who walked into my shop, bought at least, did not buy anything, neither the watch nor the camera. Clear? So there are different ways to denote this. So this is A union B, this is A intersection B. Now I would suggest that you pause the video for a few moments and look into this question. For this Venn diagram, you have to identify the following regions. First, A complement intersection B. Second, A complement intersection B complement. Third, A intersection B whole complement. And fourth is A union B, the whole complement. Let's put it an example of words. Say first is, let's stick to camera and watch. So the first one talks of those people, what is the count of the people who do not buy camera, intersection, buy watch. The second is intersection of those people who neither buy the camera as well as do not buy watch. The third is, I take all those people who buy both the gadgets, camera as well as watch, and take the complement of it. Okay, that is those people who do not buy both the items. How many of the customers that walk into my shop are those who have not bought two items? And the last one is A union B, the whole complement, that all the people who bought at least one thing and a complement of that. Hope you have given it a try how to solve this problem, and let's discuss it in detail to see why you are correct. The first one, A complement intersection B. So let's first draw our universe. Okay, our universe consists of set A, all the acrobats, and set B, all the baseball player. For this, we assume that there are certain number of people who play baseball and they are not acrobats. We are just choosing acrobats and baseball because A is for acrobats and B is for baseball. What do we have to do here in the first case? We have to calculate A complement intersection B. So let's first find out what is, say, this set is B, the baseball players, and this set is A, the acrobats. First find out what's A complement. So this whole circle is A. Anything outside this is A complement. So all this region, all this region is A complement. Everything outside this circle is A complement. Okay. And what is B? Let's draw another diagram. B is this circle. Okay. This whole region is B. Now what do we have to do? We have to find the region that is common between this first diagram and the second diagram. First is A complement, second is B. So which region do you think is common to both of them? It is actually the region inside circle B but outside circle A. So that is this whole region, just this much of a region. So I'll draw another diagram for you. So the common to the first and the second diagram is this region. This region is nothing but all those players in the class who play only baseball and they are not acrobats. So that solves our first question, A complement intersection B. Let's try the second one now. What does the second one ask for? Second one asks for A complement intersection B complement. What do? We first find A complement, then what do? We find B complement, and last we find the area that is common to both of them. So let's do that. This is our universe, this is the set A, this is the set B, and what's A complement? A complement is everything that is outside the circle A, that is this region. Okay. Similarly, what's B complement? B complement is everything that is outside this circle B, that is this region. Now, what do you think is common to both of them? Is this intersection common to them? No, this intersection is in fact not shaded in any one of them. Is this area, this area common to both of them? It is not. In the first one it is not shaded, though it is shaded in the second one. What about this one? Is this region common to both of them? No, though it's not shaded. It's shaded in the first one, but its second one it's not shaded. So what is left? Everything else that is there is common to both of them. So I draw both the circle and everything that is outside these two circles. So who are these people who are outside both the circles? These are those who are neither acrobats nor play baseball. So this answers our second question. Let's answer the third question. What does the third question ask for? It asks for A intersection B, the whole complement. Okay, so first I have to find out what is A intersection B, and then I have to find the complement of that. Complement of that means all those people in the class who do not belong to the group of A intersection B. How do we find A intersection B? In fact, we have already done it. That is over here, this first circle. This is nothing but A intersection B. This shaded region is A intersection B. And what is complement of that? Everything that is not shaded. Everything in the universe that do not belong to this shaded region is our A intersection B complement. So to draw it again, I draw the two circles and then shade everything that is not in the common region. Okay, so this is A intersection B complement. Whom all it includes? It includes all the students in the class. First, who are neither acrobats nor baseball player. Second, who are acrobats but not baseball player. Third, who are baseball players but not acrobats. These three people. Whom it excludes out of them? All the students who play both the games. And last but not the least, we'll check what is A union B complement. Now how do we find A union B? Have we already done it? In fact, yes. It is this third diagram right over here. This shaded region is A union B, and everything that does not belong to this club is not in this shaded region, is the complement of that. So to draw that, I draw this and I take the complement of what is there in the figure above. I shade everything that is outside the circle. Who are these people? These are all those people who do not play any of the two games, or who are neither acrobats nor baseball player. So now let's look all of them together at one go. Here we go. The first one is as shown in the figure above. The second one is, now this is what we draw in fourth one also. So A complement intersection B complement is the same as A union B, the whole complement. This is called the De Morgan's law of set theory. We do not need to go in that detail. It's just for your information. So the second and the fourth diagram are same. A complement intersection B complement and the complement of A union B are same. This is a useful thing to know. So from this we move on to probability. Suppose in that class, we have 100 students. So our universe is of size 100. Let's stick to A and B itself. So the acrobats and the baseball player. So there are say 50 acrobats and there are say 60 baseball players, and there are 10 students in the class who are both acrobats as well as baseball player. So how many students in the class are acrobats but not baseball player? That's easy to figure out. That's 50 minus 10, and that's equal to 40. How many students are there in the class who are baseball player but are not acrobats? That's also easy to figure. 60 minus 10, 50. And then how many students are there in the class who are neither acrobats nor baseball player? That comes out to 0, because 40 plus 50 is 90 plus 10 is 100. So all the students are accounted for, and that leaves us with 0. Let's change the numbers a bit. Let's make it 110 students in the class. Let's keep the acrobats and the baseball player and the common one same. So we have 10 students who do not play either of the two games. Now suppose you walk in at class at any point of time and all the students are there in the class. You don't know any one of them. You have no idea which one of them plays an acrobat, which one of them plays baseball, and so on. And you pick up a student at random. Now what are the chances, that player is an acrobat as well as plays baseball. What do you think would that be? How many students are there in the class? 110 of them. Out of them, how many are acrobats as well as baseball player? 10 of them. So that is 10 out of 110. So that is the probability, 1 in 11 or 0.909 of you 0.0909 of you picking up a student and he turning out to be a baseball player. What is the probability that you pick up a student at random in the class and she is neither an acrobat and does not play baseball as well? That would again be this 10 out of 110. What is the probability that you pick up a student at random and she is an acrobat? That will be this 50 upon 110. Similarly for baseball, 60 upon 110. And now suppose you want to know whether when I pick up a student, what is the probability that she just plays baseball and she is not an acrobat? So that will be 50 out of 110. So what is probability exactly? Probability is nothing but strength of a belief. You have some data and you believe that, if I pick that up, what would that be? What can it be? What is the chances that that fellow would be a baseball player or an acrobat or something? So that is what probability is. Can probability be greater than 1? That's not possible here, because you can only be 100% sure of an occurrence of an event. It cannot be more than that. Can probability be less than 0? No, you can be sure that an event cannot occur. That's 0%. It cannot go below that. It cannot be negative. You can say whether it's going to rain tomorrow in Wisconsin or not, given that it's month of September, based on what has been happening in previous years. So either if you're 100% sure that it's gonna rain, then the probability is 1. It cannot be more than that. Even if there's gonna be a hurricane or a sandstorm or something, lot of rain is gonna happen. But the question is whether it's going to rain or not. That's yes or no. And suppose you're in Texas, in Houston, and you're not sure. And you're sure that it's that month when it never ever rains. So if you are asked to take a guess, what is the probability that it's going to rain tomorrow? You will say almost nil, like as close as 0. It cannot go negative even if you are in the mid-Sahara Africa. So that's clear. So 3 things are important. Probability can never be less than 0. Probability can never be greater than 1. And lastly, the probability of occurrence of an event plus its non-occurrence, they will always add up to 1. Either it's gonna rain tomorrow or it's not gonna rain tomorrow. So if the probability of occurrence that it's gonna rain tomorrow is half, then what is the probability it's not gonna rain? It's 1 minus half. It's again half, adding up to 1. Suppose if the probability that it's gonna, it's gonna snow tomorrow in New York is 1/3. So what is the probability that it is not going to snow in New York tomorrow? 1 minus 1/3, that is 2/3. Nothing else is possible. These are the 2 events that we're talking of, either yes or no. Or we can take three cases, either it's gonna be a dry spell, or it's gonna rain, or it's gonna be windy, or dry, rain, or snow. Assuming that 2 events do not occur. It's not possible that it's dry as well as it rains tomorrow. Or, let's keep it simple that any of these 3 events is going to occur, but nothing else can occur and no 2 of them can occur. So suppose the probability of a dry spell is 1/3. Probability of it going to rain is, say, 1/2. So what is the probability of it going to snow? Would be 1 minus 1/3 minus 1/2, all adding up to 1. So these are called mutually exclusive events. When I say if one occurs, the other does not occur, it's called mutually exclusive. When I say if it's gonna rain, it's not going to be sunny. So these 2 are mutually exclusive. Or if it's going to snow, it's neither going to be rainy or it's not going to be sunny. So these 3 are mutually exclusive events. If I say that apart from these 3, nothing else is going to occur, then we say it's not only mutually exclusive as well as exhaustive. All the possible outcome has been taken care of. So mutually exclusive and exhaustive events. So 3 things we know now. Probability of occurrence of an event is always less than equal to 1. Second, it's always greater than or equal to 0, and the sum of probability of all the possible mutually exclusive and exhaustive events is 1. There are three views of probability. There is the classical view, there is the frequentist view, and there is the Bayesian view. So let's say I toss a coin. What all can happen? Either it's going to be head or it's going to be tail. So if you know the coin is unbiased and you have to put money on it, so what would the probability on head be? It will be half. What will be a probability of tail be? It will be half. So the two possible outcomes of this event is going to be either head or tail. Okay, these are the two occurrences. This is my sample space. Can anything else occur? It's highly unlikely that the coin is going to be vertical if I toss like that. Okay, so this is my sample space. The probability of occurrence of head is half. The probability of occurrence of tail is half. Is anything else going to happen? No. Can both of them happen together? No. So these are mutually exclusive and exhaustive events, each being half, adding up to 1. Suppose instead it's a biased coin, biased more towards head. Say the probability of head is 2/3. What do you think will be the probability of tail? It will be 1 minus 2 by 3, that is 1/3. That is the classical view of economics of probability. Either this happens or that happens. Let's say you roll a dice. What all can you get? It's a 6-faced dice. You get either 1, 2, 3, 4, 5 or 6. So my sample space is what? All of them, 1 to 6. What is the probability that you will get 3? It is one element out of those 6 elements. So that is 1 out of 6. What is the probability that you are going to get a prime number? So which are the prime numbers over here? The prime numbers are 2, 3 and 5. 3 of those 6 numbers are prime number. So 3 out of 6 equal to half is the probability that you are going to get a prime number. What is the probability that you are going to get a composite number? There are only 2 composite numbers here, 4 and 6. So the number of favorable outcomes are 2, 4 and 6. So 2 out of all the possible outcomes, 6. That is 1/3. That is the probability that you will get a composite number. This is the classical view of probability. So we know what is a sample space. Sample space is all the possible outcome of an experiment. We know what's an event. Event is, say, are we talking of prime number? Are we talking of composite number? We are talking of even number. We are talking of odd number. Event is like we decided what is going to happen. Is it going to be prime? That's an even. Is it going to be composite? That's an even. Is it going to be odd? That's an even. Is it going to be an even number? That's an event. So probability of an event is the sample size of that event divided by the sample size of the entire sample space. This is the classical view of probability. Now let's take a step ahead. Tomorrow, what is the probability that you are going to get married? Can I say that either you are going to get married or you are not going to get married? So my sample space is either yes or no. So just 2 outcomes, and one of the event is that you are going to get married. So your probability is half. Is that true? No, that's not how it works. Then we move to what is called the frequentist view of probability. So suppose we take data in New York, that on say 25th December, out of the last 100 years, then how many days it has snowed? Then I say out of those, in those 100 data points, on 98 of them it has snowed. So then we say the probability that it's going to snow in New York on this December 25 is 98 upon 100, 0.98. That becomes my frequentist view of probability. To the Bayesian view, we will come later. An example to do this would be, let's take a deck of cards. How many cards are there in a deck? There are 52 playing cards. How many of them are red in color? 26. How many of them are black in color? 26. So, if all the cards are shuffled, well shuffled, and I pick out a card at random from it, what is the probability that it's going to be a red card? 26 out of 52, which is half. What is the probability that it's going to be a black card? Again, 26 out of 52, a half. Now, there are 4 kinds of cards. There's heart, which is red in color. There's spade, which is black in color. There's club, which is black in color, and there's a diamond which is black in color. There are 13 hearts, 13 diamonds, 13 spades and 13 clubs. I pick up a card at random. What is the probability that it's going to be a diamond? So there are 13 out of 52. 13 cards are diamonds in a set of 52 cards. So the probability is 1 by 4. That's what the first question. Now what's an ace? There are 4 aces. One of diamond, one of club, one of heart and one of spade. So if I pick up a card at random, what is the probability that it's going to be an ace? Simple. 4 out of 52. The ace of diamonds. Now how many ace of diamonds are there? Just 1. So 1 out of 52. And the last question, it's either a jack or a queen or a king. Now can there be a card which is both jack or queen or queen or king or jack or king? No, these three are mutually exclusive events. So I can just take each of them. Like this sample, this event will have what sample size? How many jacks are there? 4 of them. How many queens are there? 4 of them. How many kings are there? 4 of them. 4 plus 4 plus 4, 12. 12 out of 52. That is 3 out of 30. Again, this is something called the addition rule of probability, which comes from the Bayes theorem. So let's take the example of the acrobats and the baseball player again. In that same class, there are 100 students, and let's say there are 40 acrobats and there are 50 baseball players, and there are 20 students who are both, so there are 20 only acrobats and there are 30 who are only baseball players. So how many are left? 30 plus 20, 50 plus 20, 70 is inside the circle. So outside the circle, 100 minus 70, 30. Now you walk in and you pick up a person at random, and the probability that she is a baseball player, so that will be 50 out of 100. Again, you walk in the class and the probability that she will be an acrobat will be 40 out of 100. Okay. Now suppose you want to figure out what is the probability that she is either a baseball player or an acrobat. So can I do 40 plus 50 to get that? No. If I do 40 plus 50 to get all the students in the class who are at either an acrobat or a baseball player, I would make a mistake, because there are 20 of them, which is common to both of them. So this, when I do 40 plus 50, this 20 gets added twice. So I need to subtract it from 20. So 40 plus 50 minus 20 is 90 minus 20 is 70, which is 20 plus 20 plus 30, that is 70. So I need to subtract this fellow out. Similarly, if we are calculating probability, so this is, if I do it in terms of set, then this is called NA union B is equal to N of A, the number of elements in set A, plus number of elements in set B, minus number of elements in the set A intersection B. That is equal to the number of elements in the set A union B. If I convert this to probability, then the probability of picking up an acrobat is 40 out of 100. The probability of picking up a baseball player is 50 out of 100. And the probability of picking up someone who is both is 20 out of 100. So what is the probability of picking someone who is at least one of them, who is at least a baseball player or at least an acrobat? That will be 40 out of 100 plus 50 out of 100 minus 20 out of 100. That is 70 out of 100 is equal to 0.7. This is called the addition rule of probability. We have covered the addition rule of probability. Now we will do two important topics in probability. One is independence of an event, and second is conditional probability, before getting into the Bayes theorem. So what are two independent events? Suppose I have a coin and a dice. I toss the coin and I roll the dice. Will a coming of head affect what is going to come on the dice? No. Will a coming of tail on the coin affect whether it's going to be an even number or odd number on the dice? No. These are two absolutely independent events. You attempting the next probability question and being able to solve it, does it have anything got to do whether it's going to rain in next 1 hour in Los Angeles or not? No. These are two absolutely independent events. The occurrence of one in no way affects the occurrence of other. Okay, so in such a case, when I say probability A intersection B, that event A has also occurred and event B has also occurred, that is equal to probability of A times probability of B. Let's take a simple case. What is A? Is the event that when I toss an unbiased coin, I get a head. So what is the probability of that event? It's say an unbiased coin, so half. And the next is that I roll a dice and I get say 3. What is the probability of getting a 3 when I roll a dice? It is 1 out of 6. So I do both this experiment together. With one hand I toss a coin, with the other hand I roll a dice. So what is the probability that I get a 3 on the dice and a head on a head on the coin? That is probability of A intersection B. Since they are independent, it will be 1 upon 2 into 1 upon 6, which is equal to 1 upon 12. That's how we calculate the probability of occurrence of two independent events simultaneously. Had they not been independent, then we would have done it differently. Which way? Probability of A intersection B would be probability of A plus probability of B minus probability of A intersection B, and so on and so forth. Here we have a question. 2 dice are thrown. Find the probability of rolling a 5 on both dice. We play that, some game where, getting both 6 or both 5 or getting a twin number gives us more point in a casino or somewhere. Then what is the probability of getting 5 on the first dice? It's 1 upon 6. Now, if I get 5 on the first dice, does it in any way affect what I'm going to get in the second dice? No. So what is the probability of getting 5 in the second dice? It's again 1 upon 6. So what's the probability of getting 5 on both the dice? It is 1 upon 6 into 1 upon 6, that is 1 upon 36. It's all, the basic understanding of what independence of two events are. Now let's move to what is something called the conditional probability. Conditional probability means that given that something has occurred, what is the probability of occurrence of another event? Suppose I pick up a card from the deck of cards. Okay, if I ask you what's the probability that it's a heart, you can't see the card. I'm asking you what is the probability it's a heart. How many cards are there in a deck? 52 of them. How many of them are heart? 13 of them. So what's the probability? 13 out of 52. That is 1 out of 4. But let me tell you something. The card that is there in my hand, it's a red colored card. Now I ask you, what is the probability that it is head? Will your answer still be 1 upon 4? No, it will change now. Why? Because your sample size has shrunk. You know that in a deck of cards, there are exactly 26 red cards, out of which 13 are hearts. So your answer will no more be 13 out of 52, but it will be 13 out of 26 or half. So given that in my hand it's a red card, the probability of it being heart is half. Instead, if I said that no, it's not a red card, it's a black card, then what's the probability of it being a heart? 0, because there are no black hearts in the deck of cards. Okay, so that is what conditional probability is all about. Given that an event has occurred, what is the probability that another event would occur? Given that Trump has been elected, what is the probability that a certain economic policy would be implemented? Or given that Hillary has been elected, what is the probability that a certain economic policy is implemented? The answer to both the questions would be different. Okay. So what is the formula for this? So this is over here, probability, the way to write is probability A given, this line means given B. Probability that my card is heart, given that it's red, is 13 upon 26 or half. Instead, probability my card is heart, given that it's black, is 0 upon 26 or 0. So this is what is meant by this vertical line. It is said as given that. And what is the formula for that? So there's a formula which we will go through and try to understand how it works. This is the formula. Probability of A given B is probability of A intersection B divided by probability of B. Let's do it again by the card example. Probability of a heart given that it's a red card is equal to probability of heart intersection red divided by probability of red. So what's probability of red? I pick up a card at random. What is the probability that it's a red card? It is 26 out of 52, equal to half. The upper question is, I pick up a card at random. What is the probability that it's both heart and red? That is 13 out of 52, because there are 13 cards which are heart and all of them are red. So equal to 1 out of 4. So what is the probability it's a heart given red? It is 1 out of 4 divided by half, or equal to half, which is same as what we figured out by a simple analysis, that given that it's a red card, there are 26 of them and 13 of them is heart, so it will be 1 out of 2. So this is that simple formula. Now suppose, here, are occurrence of a heart and red independent events? No, because heart is a red. If I know that the card in my hand is red, then I can say something, my probability of it being heart changes. If I know that the card in my hand is black, then the probability of it being a heart changes. These are not independent events. Okay, but instead, if the question was that I roll a dice and I toss a coin, and I say that in the toss of the coin I have got a head. So what is the probability that when I roll the dice I'll get a 5? It doesn't matter, whether head came or tail came, it won't affect what is going to come on the dice. So probability of A intersection B becomes probability of A times probability of B. And if I put that in this formula and divide it by probability of B, then this probability of B gets cancelled, is equal to probability of A. So when I have an event, probability of A given B, and A and B are independent events, that will be same as probability of A. So here is how we marry both the concept of conditionality and independence together. Okay, so now let's take this formula 2 steps further. We are trying to move to the base formula. Okay, so before we get there, let's write this formula like this. Probability of A intersection B is probability of B times probability of A given B. This is nothing but taking the denominator over here and doing cross multiplication and moving it that side. So that gives us probability of A intersection B is probability of B times probability of A given B. Now suppose instead if I want to write what is probability of B given A. Probability of B given A by the same formula is probability of B intersection A divided by probability of A. But we know that probability of B intersection A is same as probability of A intersection B, which is this. So I substitute that over here, and that gives me probability of B given A is probability of B times probability of A given B divided by probability of A. So this is what we are moving towards the base formula. So I have written this here in terms of F and E, the same formula. So over here probability of F given E is probability of E given F times probability of F divided by probability of E. So this E and F reverse, and whatever is given over here is what it gets multiplied with. Now there's another rule, in probability that will help us expand the denominator. That's called the law of total probability. Okay, so what is that? So when we say probability of occurrence of an event is same as probability of occurrence of that event intersection another event that has occurred plus probability of occurrence of that event intersection another event that is not occurred. I've written C over here, which is same as complement. It could be written as dash as well. So let's understand this formula first. This is called the law of total probability. Let's do it in terms of the set diagram. Okay, suppose this is event E and this is event F. event E, event F. So this is my whole universe. So if someone asks, what is probability of E intersection F? That is very simple. That is this event, that both the event has occurred. And then if someone asks, what is the probability of E intersection F complement? That would mean F has not occurred, but E has occurred. That would be this event. Okay, this is the region where F does not occur, but E occurs. So this is E intersection F dash or F complement or F superscript C, and this is E intersection F. Now what happens if I add these two diagrams together? The shaded regions add up together to give me this region. Now what is this region? This region is E, the entire E. So this is what this equation is all about, the law of total probability. So probability of E is probability of E intersection F plus probability of E intersection F complement. And we already have a formula for this. For any P A intersection B, we can write it as probability A given B times probability of B, or probability B given A times probability of A. So we write probability of E intersection F as probability of E given F times probability of F. Similarly, we write probability of E intersection F complement as probability of E given F complement times probability of F complement. So combining this equation 1, this equation 2, this equation 3. So we substitute 2 and 3 in 1 to get this denominator over here as a replacement of probability of E. Okay, so the numerator remains same when we move from here to here, but the denominator gets expanded as explained above. This is called the Bayes theorem. Now, how do we use it? We have a very good question for that. So this is it. Suppose in any given society, say in a particular state, that only roughly 0.5% of the population has HIV. So I pick up a person at random. What is the probability that the person has HIV? That would be 0.5 divided by 100 is equal to 0.005. And then a person at random walks into a test clinic and gets tested for HIV. What is known about HIV test is that if a person comes for an HIV test and the person has HIV, then in 98% of the cases it will detect it. Okay, it's 98% effective. But there is something as false negative rate. Okay, that is the person has HIV, but in every 2 of those 100 individuals, it will say that the person does not have HIV. So out of every 100 people that come for the test who have HIV, given that they have HIV, in 98 of the cases, the medical test says yes, they have HIV. And in 2 of those cases, the medical test says that no, they do not have HIV. Another thing is, given that the person does not have HIV and walks into the clinic to come for a test, then 1 out of all those 100 people, for them, the test says that the person is HIV positive, even though the person is not HIV positive. So let's say a person comes in, tests for an HIV, and the test shows positive. Should the person be worried? Of course, he should be worried. But, how worried should he be? That given the test has been positive, what can we say that the person has HIV or not? What's your guess based on this value? Make a guess, then try to solve this problem, and then we'll discuss and let's see how close we were to that guess. I hope you have given the problem a try. Now let's try to solve it together. What does the question say? The question says that an HIV test is 98% effective in detecting HIV. That if someone has really HIV and comes for the test, then in 98 out of the 100 cases, the test would say, yes, the person has HIV. But in 2 of those 100 cases, that is 2% of the cases, even though the person has HIV, the test may not be able to detect it. That is the false negative case. Another thing, there is a false positive thing. a person who does not have HIV and comes for a test, in just 1 out of the 100 cases, the test would show that the person has HIV. Plus, the last data point is that in the population that we are talking of, only 0.5% of the population, or 0.5 divided by 100 probability, is of picking a person at random from that society, and that person may have HIV. What is E over here? That a person tests positive for HIV, and F, that the person actually has HIV. And what do we want to calculate? We want to calculate probability F given E. That means someone has gone for a test, the test shows positive, then what is the probability that the person actually has HIV? So what I need to calculate here, using the Bayes theorem, we just reverse this. Okay. What do we know? Do we know PE given F? What does this mean? That the person actually has HIV, that is known, and the test shows positive for it. Do we know this? Yes, we know this. That is this 98%. PE given F is 0.98. So when I do the formula is, which we have already discussed using Bayes theorem, I just reverse what is here. Whatever is here, I reverse it. F given E becomes E given F times whatever is there in the given part. So P of F, this whole divided by, now I repeat whatever I wrote over here, I write it again. P E given F times P of F plus the complement of this lower part, the given part, P E given F complement times P of F complement. Now let's see whether we know each of them or not. PE given F we know is 0.98. What's P of F? What's F? That a person chosen at random actually has HIV. That is what? That is this 0.5% of the population. So 0.005. So if PF is 0.005, what would be PF of complement? That will be 1 minus this, or 0.995. One last thing that remains is PE given F complement. PE given F complement. What does F complement mean? F means that a person actually has HIV. F complement means that the person does not have HIV. So, and E is that the person actually tests for HIV. So that is which number? This number. The person does not have HIV, yet the test says that the person has HIV. So that is P E given F complement, which is 1 upon 100 or 0.01. So far so good. Let's put in the values. PE given F is 0.98 into P of F is 0.005 divided by the same thing plus something more in the denominator, and what is that? That is PE given F complement, which is 0.01 into F complement 0.995. That's it, as simple as that. You know how much this value comes to? Around 33% or 0.33 probability over here. So, you know, at the onset it may seem that if the person, the way the problem looks is, you know, if the person shows HIV positive and the test which is 98% effective, it's highly likely that the person must have HIV. But as we can see, it's not even 50% of the cases that such a person would have HIV. So, you know, one cannot say that one need not be worried about, but it's not such a grim scenario, probabilistically speaking.
Acadgild. Average is dead.